In this lecture, we're going to be switching gears, so we're actually moving now into the part of the course that's going to be talking about convection. Through the first 11 lectures, have basically dealt with energy balance through understanding resistances just in their general form, and then dealing with conduction problems, both for steady state, non-steady state, and in 1 and 2 dimensions. The principles that we learned in the first part of the course related to Fourier's law and rates are going to apply here as well, but there's just a different kind of approach that we're going to take for the convection problems, and so that ends up looking a little bit different. So in this part of the next few lectures here for this part of the class, we'll be talking about what convection means, how we model it, and how we can think about it in a way that lets us actually anticipate temperature profiles in a bit more detail than what we had before. So if you remember last time, just as a quick recap, we wrapped up our numerical solutions to transient problems. So for these, what we were expecting to do was to develop a state equation that lets us predict the temperature rate of change with respect to time, and then use that to take a step forward, a numerical step forward over some finite time step to predict the temperature in the coming time, and then just continue on until we've sort of gone far enough where we're happy. We talked about a couple different methods to do this. So one is Euler's, the other is Hoyne's method. Euler's method is an explicit technique where you just estimate the derivative at the beginning of the time step, whereas Hoyne's method is a predictor-corrector method, which includes an estimate at the end of the time step, and then you average both of those derivatives together. In both cases, what you're trying to do is develop the state equation, and that state equation is useful for predicting the rate of change that lets us step forward in time. We did extend this to 1D transient and had an example with that. So we are now, like I said, putting aside our conduction problems for the time being and thinking about this idea of convection. So far in the class, when we've talked about convection, we've basically been dealing with Newton's law of cooling, which is this rate equation that looks something like the following. So it's a Q dot convection, the heat transfer by way of convection, is equal to some heat transfer coefficient, h bar, times the surface area exposed, times the potential, T, let's call it T of the surface, Ts, minus T infinity. And if we're doing a conduction problem, maybe Ts is the temperature at the end of the domain, and we're enforcing a boundary condition. Or if we're doing just some kind of a resistance model, then Ts is the temperature of that node at the end of the resistance. But in all of these cases, we're just saying, okay, I've got this h bar, and h bar for me is something that is given to me, and I don't really know how to compute it or how it changes or what it depends on. I do want to point out that this h bar, right, this is not a fluid property. Like conductivity or like specific heat or like density are properties of the material, H is not a fluid property. So what is H? Well, H is a coefficient basically that we compute that lets us predict the rate of heat transfer given these other conditions, the surface area and the temperature difference. So it's really like a catch-all for all the physical mechanisms that are involved in moving heat from a surface to a fluid. So let's define what we mean by convection. I've written out the definition here. So convection is heat transfer or heat transport between a solid surface and a fluid that's in motion. And the mechanism of heat transfer is conduction and advection. So even though we're saying now we're moving on from conduction, convection is really just a conduction problem where we're actually introducing movement of the fluid as well. And because it's a conduction problem, because the same kind of rate equations apply in parts of the convection domain of interest, we can still use a lot of the principles of conduction to actually predict the rate of heat transfer through convection. So one of the key concepts for convection is this idea of something called a boundary layer. A boundary layer is this thin layer that develops between the fluid and the surface, And really all it is just the region of the fluid that's affected by the presence of this surface. So it's not like there's really anything special about the boundary layer. It's just the part of the fluid where you can tell that there's a wall present. So let's actually sketch out what the boundary layer looks like in terms of the velocity. So on the left-hand side over here, we have some free stream velocity. We'll call this free stream velocity. We're calling that U infinity. So if you go out at some indeterminate distance from the plate, you can't tell that the plate was there. Down here on the bottom, we have a long flat surface. Let's call that an extended plate, some kind of flat surface. And before this point x, this coordinate system where x begins, the fluid is just flowing free stream. At this point, it sort of hits this plate, and you start developing an effect, right? And so what I want to sketch out is, as a function of position x, the region that is affected by the presence of the plate. So if we just looked, let's say, let's pick this position here. If I pick this position, where let's call this x1, and I sketch the velocity profile of the fluid, right over here we have a velocity profile as uniform. Now if I sketch the velocity profile at this point, what is that going to look like? Well, out here, as you are far away from the plate, the velocity is basically unaffected, right? So you can kind of sketch the velocity is unaffected. As you get closer and closer to the plate, there's going to be this shear force in the fluid. And that shear force is going to cause the velocity to slow down. And so if we sketched out the velocity profile, it might look something like this. Right? We're out here, we're sort of at the free stream. So there's this kind of disturbed region of the domain. If we go even further, right, at x2, now we sketch the velocity profile out here, we note that there's been more room for this shear stress to kind of propagate through the fluid. So maybe very far out, you still have the velocity profile unaffected. But as you start getting closer, you're going to notice that actually the velocity profile has been affected. And so if we sketch that, it looks maybe something like this, where kind of out at this position, or say we have it here at that position, those are the positions where basically we can say that the velocity hasn't been affected. So what we can do is we'll just draw, let's kind of connect the dots here. Let's draw the distance at which the velocity profile has been affected as a function of position. And what does that look like? Well, it turns out it looks something like this. So you have this boundary layer that kind of develops like this, and it will just kind of extend out and continue to grow. And so we'll call this distance, right, this distance here, delta sub m. Right, this is the boundary layer thickness. And why are we calling it m? Well, this is actually the momentum boundary layer. So I'm going to abbreviate boundary layer BL, boundary layer. That delta m, that is a function of x, right? That is changing as a function of position. But the important thing to note is down here in this region, you're seeing a lot of really rapid growth. And then as the problem sort of continues, the growth slows down. One important thing to note is that this growth will never stop. So it will always continue to grow in this direction. And I'll talk a little bit more about why that is later. So we've talked about the velocity boundary layer. Let's also talk about what it kind of means mathematically. So the velocity boundary layer is this region near the surface where the fluid velocity deviates significantly from the free stream velocity. So there's a few things to unpack there. So let's say we've got some velocity profile, u as a function of y. Let me just scroll back up here. So we have this coordinate here, this coordinate y. I'm drawing the velocity profile. Oops. I'm drawing the velocity profile as a function of coordinate y at a given position x, right? So I pick an x, draw y. So we have a velocity as a function of y. What I'm saying is where u as a function of y is less than, let's say, 0.99 times u infinity, that's my definition of the boundary layer. So within 1% of change of that u infinity, if there's anything greater than a 1% change, then it would be as included as part of the boundary layer. So this is just a common definition that people use to describe this. So let's describe this in terms of the viscous shear that's involved, and this will help us kind of anticipate the size of this boundary layer as it grows. So if you remember back to your fluid mechanics, we'll say the viscous shear tau is governed by this equation where you have the viscosity mu times the partial derivative of velocity, the velocity field u with respect to y. All right, so shear stress is mu du dy. That should look reasonably familiar to you. What we can do here is, again, let's just come up with an approximate model that helps us anticipate the growth of this boundary layer. So our approximate model, let's say this is approximately equal to, well, mu is a fluid property, so let's keep that. What is the du that we're looking at? So look at the boundary layer as it's growing. What is the du, or the change in velocity, as a function of y? The total change in velocity, well, it's going from u infinity down to 0. So du can be approximated by u infinity. What's dy in this case? What's the distance over which that change occurs? Well, that's actually delta m, right? Delta m, which is a function of x. So we have this kind of approximate model, and we can use this to kind of help us develop a relationship, which we'll do in just a second here. Before we do that, let's think also about the thermal boundary layer. So the velocity boundary layer grows away from the plate according to the region that's disturbed in terms of the velocity profile in y. You can do kind of the same thing for temperature profile. But out here, let's say we've got some uniform temperature coming in. Again, I'm going to pick x1 and x2. And what's happening here is, let's say that this plate that it's running over has a uniform temperature T sub s. Right? T sub s is held constant over the entire length of this plate. What you end up with is once the fluid hits this plate, the fluid right at the edge of the plate will immediately become Ts. Right? It becomes Ts. It's held at that temperature. But then you get this thermal wave that propagates. And it's really very similar to the 1D transient cases where you have this thermal wave propagating as a function of time. Now it's this thermal wave propagating as a function of like the duration over which the fluid has been exposed to this plate. So what does that look like? I guess we can say, if we just plotted temperature, so I'm going to plot the temperature profile as a function of coordinate y. So out away from the plate, we're at T infinity. As you get closer and closer to the plate, let's say this here is T sub s. As you get closer to the plate, you're going to get this thermal wave that's growing. As you go further out to x2, the same kind of thing happens, but now there's been more time for this wave to grow. So this is still Ts. Right? We still have the same difference in temperature, but it's sort of occurring sooner, right? That transition to the region that's been affected is occurring sooner. So if we draw a boundary layer for this, a thermal boundary layer, that thermal boundary layer is going to intersect here and it's going to intersect here. So very much like the velocity boundary layer, you get this initial growth and then it sort of stagnates, right? It will always continue to grow in this direction unless something changes about the problem. Just like in a semi-infinite wall, that thermal wave will always continue to propagate. Right? It does so more slowly over time. So let's look at a relationship with the thermal boundary layer, like our definition of that, just like we had up here for velocity. The thermal boundary layer is going to be defined as the region where the temperature of the fluid has been disturbed in some significant way. So assuming that Ts is greater than T infinity, which is what we've sort of plotted out on the right here, we can write this like this. Ts minus T is a function of y, right? That's the temperature, like you'd say in the y coordinate over here. It's some position y, and you'd say pick a temperature, right? It's that temperature. So Ts minus Ty over Ts minus T infinity. And we're going to look for any place where that ratio is greater than 0.01, right? Which is kind of the equivalent of the velocity, but we just flipped it around because we're saying that the temperature at the wall is higher. So this is the definition of the thermal boundary layer. You can pick different values, and just depending on the convention that's used, then the boundary layer will be larger or smaller. But this is the basic idea of how we define the boundary layer, both in terms of momentum, which is to say velocity, and in terms of energy, which is to say temperature.